Good afternoon. My name is Wenxuan. Today I'll be presenting our paper, Automatically Correcting Networks with NEAT. It's a joint work with Jason Croft, Bingzhe Liu, Elaine Ang, and Professor Matthew Caesar. So the story really started with, networks today are so complex. It's hard to make sure they are doing the correct thing. What a network is supposed to do, well, that from an operator's point of view is the intent that they have in mind, what they build this network for. So we can consider a network as a implementation of a collection of corrected conditions, from conditions as simple as a loop avoidance to like prevention of untrusted traffic from entering a secure zone to even complex compliance requirements. So to fulfill those requirements, operator typically gets to write pretty complicated configurations or control softwares. And after that's done, the output got pushed to the network devices. This is not an easy job because they have to deal with codependent functions running on hundreds of thousands of devices of different types from different vendors, compounded with an increasing continuous change in an increasing pace. So if you think about a typical enterprise network today, you've got multiple sites, thousands of devices, you got WANs, cloud networks, and even within a single data center, there are multiple layers, a device of different roles, and dozens of protocols implementing features like high reliability routing and so on. So the result of all this complexity is that we see data breaches and outages over news with these company names. And the list can go on and on. And in fact, almost 9 out of 10 operators are never completely certain that their changes wouldn't introduce a new problem. So apparently, networks today are so complex and it's beyond what humans can comprehend by ourselves only. So the natural answer would be let's automate. And then the problem becomes what part of the workflow can we automate, and how far can we push the automation? So let's first have a look at what people have tried. There are basically two main streams of research. There are a variety of techniques to verify network behaviors. Those techniques basically take a set of required correctness conditions, which we will refer as policies, and some form of network abstraction. For example, configuration files, control plan, data plan, or control software, and find violations. But they stop there. They don't help operators actually repair those buggy states. Another thread is there are techniques to synthesize correct network states from scratch based on a set of pre-specified policies. So they are good in the sense that the network states are correct in the first sense with regard to the policies, but they are developed in for use similar to a compiler. So when the policy changes, you need to do this again, and thus they operate offline typically. So that makes us think, what if we can automatically repair networks? So we take the policies, we take the network abstraction, we automatically correct them while it operates. So basically, we want autocorrect. That is a term that's familiar to all of us. I guess we are using that on our smartphones every day. But this time in the context of networking, and with more focus on software-defined networks in this work, we are proposing network error autocorrect NEAT. And in particular, this work, we look at the problem from data plan, simply for the reason that given this layered network device view, data plan is the narrowest, and so analyzing data plan can allow us to uniformly analyze the result of multiple control plan protocols. And we are sitting as close as possible to the actual network behavior so we can capture the upper layer bugs and fix them. We are aware there are efforts on automatic repair other layers, for example, CPR, and we think those efforts can be used in complementary manner. Okay, so let me restate the goal of designing NEAT. We want to provide a system that automatically repair network updates, keep the network state consistent with the desired policies, and relieve the network operators from slow and error-prone process. So such a system should improve upon a manual effort with transparency in both performance and architecture. So that poses two challenges. First, on repair speed. if a repair system repaired the network using hours or days, while the process can be manually completed in tens of minutes, then the system is useless. But achieving this in a timely fashion is very challenging due to the size of the modern network and data plan states. So to address that, we first built on top of our prior work on real-time data plan verification to efficiently model and capture network violations. And then we cast the repair problem as an optimization problem. To further speed up the repair process, we developed two techniques to shrink the size of the optimization problem. Challenge 2 is such a system ideally shouldn't require modifying existing applications or changing the current infrastructure. So if an update is introducing a violation to some property in the network, we should fix the update, fix the cause, while trying to maintain the original purpose of that update. So for that, we argue keeping the changes minimum is necessary. And the system shouldn't burden the operator or users with the task of modifying their applications. But for those who want to have a finer-grained control of the repair process, we should have the option for them to do so. So we provide two modes for applications to interact with our system. So with those two guidelines in mind, here comes the design of NEAT. Basically, NEAT operates as an intermediate layer between controller applications and the network devices. It takes policies like reachability, segmentation, or waypointing in the form of directed graph, and as well as the updates streamed down from controller applications. So if an update doesn't violate any policy, it's sent onto the network. Otherwise, it's corrected by NEAT before reaching the network. All right. So let's zoom into NEAT a little bit. So inside NEAT, the foundation is the network model and the verification engine built on our prior work, which first symbolically slice separate, like divide traffic space into symbolic packet sets. Packets within each sets are forwarded exactly the same manner throughout the network, and that forwarding behavior is modeled as a directed graph. So upon verification engine detect the violation, the relevant updates are handed over to the correction engine, which is the core of NEAT, which is in charge of correct that updates send the corrected version to the network and update the network model accordingly. So next, I will visit individual components in this diagram, starting from the controller application and NEAT interaction. So as previously briefly mentioned, we provide two modes for application to interact with NEAT. On the right-hand side is the simpler one, the pass-through mode. Application operates on that mode is not required to be modified. In fact, they are unaware of existence of NEAT. So NEAT serves as a transparent layer, intercepts updates and correct it if necessary. And on the other hand, the interactive mode is more complicated. It allows the application to use NEAT API to leverage the API to propose updates and keep its own state consistent with the network state. So application can propose a set of updates to NEAT, and NEAT will verify that against the model. And if there's a violation, NEAT suggests the replacement of that set of updates to application, which application can accept or reject. If the application accepts that the update is sent to the network, and the application can update its own network view. Otherwise, the application can propose another set of updates to NEAT. A note here is, as this diagram shows, application with different operating in different modes can simultaneously run on the same instance of NEAT. So next is the policies, the second source of input to NEAT. So we initially thought about reason the network on the basis of paths, as we did, and also other verification tools did. But we found out that sometimes it's incorrect. Synthesis network changes actually requires us to view the network as a whole, because if you change a path, repair a path, the changes may affect the correctness of other paths. And in addition, if we express the policies in the form of graph, then we can deal with a richer set of policies, like load balancing, which reason about the dependencies between paths. So NEAT takes a set of intended policy and formulate them in the form of a directed graph, which we call a policy graph. And each policy graph is defined on a packet header pattern. For example, HTTPS traffic towards this IP destination prefix. So a packet policy graph edge is denoted with notations that captures different reachability requirements. For example, this edge from A to B requires that exists at least the m path, so m is the path count, exists between A to B, and each of the paths is bounded by n hops. And here A and B are traffic footprint, or say traffic header pattern at a certain network location. So with this edge in place, we can express basic reachability policy with an edge by assigning m with 1. And and n unspecified. When we specify an n, then we get bounded path length policy. When m is assigning with a larger integer larger than 1, then we get multipath policy. And whereas when m is assigned with 0, then we want to enforce that A should not reach B. These are supposed to be isolated. So furthermore, when we're concatenating edges, we are like in this figure, we are showing service chaining, or say waypointing policy. For example, this A to C traffic should traverse B first before reaching the destination C. Another case worth mentioning is load balancing here. So as a load balancing policy typically involves a way to distribute traffic among a pool of servers. So here in our policy model, we assign a path count with a fraction of value instead of those integer value in this case. For example, this policy graph is enforcing a policy that traffic from this client C got evenly distributed among these 5 servers. So as such, NEAT use policy graphs to express both qualitative and quantitative reachability constraints on the graph. So next is with these policy constraints, how can we repair the erroneous network state? So as briefly mentioned, when upon intercepting update from the network application, NEAT first slice the affected packet space into equivalent sets, and for each of them we model the forwarding behavior as a directed graph. So on this network state graph showing up here is the one configured like forwarding graph together with the topology. You see those edges with arrow are the forwarding graph. Those one without arrows are the topology and links. That together with the policy graph serves as the inputs of our repair algorithm. So we cast the problem as an optimization problem to minimize the number of changes in the original configuration graph. The goal is to change the graph in a way to make it mappable to the policy graph. So let's start from the basic reachability case, the simplest one. So basically we create one Boolean variable between every topology edge, topology link, and the policy graph edge. If the Boolean variable is assigned with 1, that means that the topology link is used to forward traffic for the relevant policy graph edge flow. For example, we see there's a C to J edge required on the policy graph. That means we should have a path from C to J on the network state graph. And we see there it is there. And similarly, for K to J policy graph edge, we are trying to find a path from K to J, and it's absent. So that means to properly repair this the network state, we should have that path added. More formally, we are solving this optimization problem with constraints posed by policy level reachability as well as the topology, the physical topology constraints. So for basic reachability, we have this set of constraints. And of course, we are not going into this level of details, but on a slightly higher level. So we have a set of equations saying no physical link should be used to forward traffic for the same flow on both directions. So there's no tight loops. And for every policy level reachability, we have a set of flow conservation equations to ensure those. And to support a generalized reachability policy, for example, rich isolation, service chaining, or multipath, we encoded several additional equations into the constraint sets. Just to take two examples. For service chaining, we encode one additional equation into the flow conservation equation set to enforce the waypoints are traversed in the correct order. And for load balancing, for example, we have additional equation to make sure the flow distribution propagates satisfy the policy requirements. Okay, so you maybe already noticed that I'm missing some important policy, and actually I've been ignoring that policy on purpose. So that is the loop freedom. The preceding algorithm actually operates on a loop-free configuration graph. As such, the procedure we repair graph actually is first we look for and remove loops before repairing violations of any other policy types. So the goal is the same: minimize changes in the network configuration and the configured graph. So with the preference of affecting as few packets as possible. For instance, we will prefer to remove a rule matching packets destined to 10.0.0.1/32 over a less specific rule, 10.0.0.0/8. All right, so now we have a way to repair the buggy network state, data plane state. However, while conceptually straightforward, this doesn't scale to large network. The reason is simple, just doing the math that the number of variables of every formulation of the problem, the optimization problem, is approximately the product of the number of edges on the topology graph and the number of edges on the policy graph, which can easily exceed 100K in the moderate fat tree topology for all-pause to all-pause reachability. So what shall we do? Okay, so let's take another look at this typical enterprise network diagram. So we can see that there are the network is designed to enforce certain symmetry to some extent. So you can see those sites are kind of symmetric to each other, and those two core routers are mirroring each other on some level. Another interesting finding is that the network is also structured in a hierarchical way. We saw those it's divided into sites, and those sites are connected by the backbone network. And so that means that implies some certain communication pattern. Typically, for example, communication within one subtree, one site will stay local, and communications between subtrees won't traverse another subtree. So it doesn't go through a valley and going up. So based on this architecture structure, after we detect the violation, before we form the optimization problem, we first slice away the irrelevant or redundant part of the network, and that we refer as topology limitation optimization. In addition, we also explored the symmetric pattern, or say regularities in the graph, to further compress the graph that the optimization problem is dealing with. So the key of the compression would be the compressed graph should be equivalent to the original graph with regard to the policies of interest. For that, we leverage algorithm from a graph database literature as the major building block. And that algorithm basically compressed the labeled directed graph based on bisimulation relation. But for the details of this algorithm and our how we customize the algorithm for our special need and how we encode our policy into the labels and also the proof of the equivalence, please refer to our paper. Oh, okay. So next is the implementation. We implement that in a prototype in Python. I will skip the detail of that. So we have examining the NEAT when it's working with Mininet and POX, running two applications, one in pass-through mode, one in interactive mode. So this diagram shows the interactive application perceived end-to-end delay when NEAT is there to verify and fix errors. We can see that in the largest setting, when we use both techniques, both optimization techniques, NEAT is able to repair and detect and repair the error within 120 milliseconds. And we next examine NEAT when it's working with real network trees of 1 million folding entries. So we enforce loop freedom and management address, pairwise management address reachability. And NEAT has found and repaired issues, including loops caused by default routes, lack of default routes, and load balancing feature that shouldn't be turned on that actually cause both loops and partial paths. The last set of experiments I'm showing here is so we cut a clear line between repair and synthesis in the context of this work, but we think there's a connection between them, and thus we compare NEAT with a synthesizer. So I will skip the detail, but the high-level takeaway is in both of them using as a repair or both of them using as synthesizer scenarios, NEAT achieves 2 to 3 orders of magnitude improvement. All right, so to sum up, NEAT, we propose NEAT system automatically repairs the network state analogous to a smartphone's autocorrect feature. So we think this is definitely not the end of the story, but the start of the thread. There are a number of directions we want to explore in the future. Firstly, in practice, policies are changing over time, so we will want to examine NEAT in that scenario, and we would like to study ways to express more richer policies. And secondly, in our current normalization, the goal is to minimize the number of edits, which may not be the ultimate desired goal. We want to explore other goals. And lastly, we want to study ways to infer the context of updates to improve repair relevance. Okay, yeah, I would like to take questions.
Aaron Geber-Jacobson, Colgate University. So you talked about these two modes, this sort of passive and interactive mode. I guess maybe it's more of a concern in the passive mode, but if you're changing things in the data plane and the controller isn't aware of that, do you end up with some sort of conflict where they're each trying to make changes, the repair and the app, and they just end up in this infinite loop?
Yeah, there are several. Yeah, that's a very good question. And actually, we got that question a lot. So there are several parts of the story. If the application has its own state maintained, we recommend it's operate in the interactive mode instead of pass-through mode. And also when they have absolute conflict interest of in the application and the network, NEAT is actually guarding the safety of the network by rejecting the application. So in that sense, it's not terrible. It may be more desirable to have the application intents rejected.
Yeah.
So I'm not sure I completely understood the work, but is what you're doing that if there's an error in the data plane, you're trying to fix the data plane? Is that what you're trying to do?
That is what we are doing. We are thinking this repair work is more in the scope of a very urgent and temporary fix that you don't have the time window for human intervention. And for the full fix, you may left out for human to look into the configuration to fix the root cause of that.
Yeah, so my concern is if you don't really do the root cause, then the next time there's an update to the network, the data plane changes again, and there's probably another error. So is it like you're almost always going to be in some error state and trying to fix it?
Sorry. Yeah, we are not intended for using this tool for the longer term construction. So after this temporary error got prevented using NEAT, we'd like the other component or the human to do the longer term. Yes, if we keep using NEAT, we not like rule out of human intervention.